E2 to E3 CM technical network optimization using DTT reports and zone data management. The agenda points are radio network optimization, optimization of the cost and guaranteeing the network service quality, efficient utilization of resources, drive test tool and parameters, zone architecture and data management. Purpose of radio network optimization. The purpose to perform optimization on the network is to maximize benefits while minimizing capital and operation cost for operators. Cell reports and KPIs. Cell reports contain thousands of statistics about all relevant behaviors such as number of attempts, failures, successes, handover, setup, etc. These statistics are reported to the network management system as counters. A set of key performance indicators is defined out of formulas using counters. Each operator chooses its own KPIs and sets. Another aspect that is important in optimization phase deals with the drive tests. While statistics give a general idea of the cell's behavior at a certain period, field measurements give a one-instant scenario of one area's behavior during a call. Different tools can be used to perform drive tests. Each specific tool is able to standard reporting at the signal level, quality, and site information. Other methods. Tracing catches on object's behavior during a certain period and regarding a specific event or a set of successful events. Alarm monitoring, transition network auditing, and network switching subsystem performance follow-up are also important in the sense that they give an idea of hardware problems and parameter errors. After analyzing the statistics reports and drive test reports, actions are then taken to correct and improve performance. Field knowledge and correct site reengineering form the basis for improving the network performance. Frequency planning review is also a key step in the process. What is drive test? Drive testing is a method of measuring and assessing the coverage, capacity, and quality of service of a mobile radio network. Drive testing is principally applied in both the planning and optimization stage of network development. Drive tests are the most common measurement tool used by operators to probe the quality status and solve the network problems. The technique consists of using a motor vehicle containing mobile radio network air interface measurement equipment that can detect and record a wide variety of the physical and virtual parameters of mobile cellular service in a given geographical area. It is conducted for checking the coverage criteria of the cell site with the RF writers tool. The data collected by writers tool in form of log files are assessed to evaluate the various RF parameters of the network. The data acquired from drive test are signal intensity, signal quality, interference, dropped calls, logged calls, call statistics, service level statistics, QoS information, handover information, neighbor cell information, GPS location coordinates. Different types of drive testing are network benchmarking, optimization and troubleshooting, service quality monitoring. The equipments required for drive test are a laptop, drive test software with a dongle and license key, GPS to provide location information, one or multiple handsets compatible with the drive test software, scanner, database of existing network, a suitable vehicle. The equipment for drive test are to be connected as shown in the figure in the slide. There are Data collection tools and post-processing tools. Thames Investigation, Nemo Outdoor, JDSU E6474A, AccuWork XCal are the important data collection tools. Actix Analyzer Spotlight, AccuWork XCap, Thames Discovery LTE are important post-processing tools. LTE drivers parameters are reference signal received power RSRP, reference signals received quality RSRQ, received signal strength indicator RSSI, signal to interference noise ratio SINR, channel quality index CQI, physical cell identity PCI, block error ratio BLER, downlink throughput and uplink throughput. RSRP, RSRQ and RSSI. RSRP indicates coverage. RSRP is the average power received from a single reference signal, and its typical value ranges from minus 44 dBm to minus 140 dBm, where minus 44 dBm is good and minus 140 dBm is bad. RSRQ indicates quality of the received signal, and its value ranges from minus 19.5 dB to minus 3 dB, where minus 19.5 dB is bad and minus 3 dB is good. RSSI, or Received Signal Strength Indicator, is a parameter which provides information about total received wideband power, including all interference and thermal noise. RSSI is the sum of noise, serving cell power and interference power. RSSI is related to RSRP and RSRQ through the formula RSRQ equal to capital N into RSRP by RSSI, where N is the number of resource blocks of the E-ultra carrier RSSI measurement bandwidth. SINR is the reference value used in the system simulation and can be defined wideband SINR and SINR for a specific subcarriers, all measured over the same bandwidth. SINR equal to S by I plus N. The range of values for RSRP, RSRQ and SINR with respect to different RF conditions are tabulated here. For excellent RF conditions, RSRP value will be greater than or equal to minus 80, whereas at the cell edge it will be less than or equal to minus 100. The value of RSRQ will be greater than or equal to minus 10 if the RF condition is excellent, and at the cell edge the value will be less than minus 20. SINR will be greater than or equal to 20 for excellent RF conditions, whereas at the cell edge the value will be less than or equal to 0. The channel quality indicator CQI contains information sent from a UE to the E node B to indicate a suitable downlink transmission data rate. CQI is a 4-bit integer and is based on the observed signal to interference plus noise ratio at the UE. The CQI estimation process takes into account the UE capabilities such as the number of antennas and the type of receiver used for detection. The CQI reported values are used by the E node B for the downlink scheduling and link adaptation. Block error ratio, or BLER, is defined as the ratio of the number of erroneous blocks received to the number of blocks sent. An erroneous block is defined as a transport block where the cyclic redundancy check, or CRC, of which is wrong. WCDMA drivers parameters. Received signal code power, or RCP, is the received power on code measured on the primary CPICH. The unit of RCP is dBm. It shows the signal strength of a cell and it indicates the coverage. RSSI or Received Signal Strength Indicator is the wideband received power within the relevant channel bandwidth. It is a parameter in dBm that describes the total signal strength of a ultra carrier frequency. In other words, the signal strength of all cells of same frequency at a certain location. EC by NO. It is a parameter in dB that describes the received energy per chip divided by the power density in the band. The measurements shall be performed on the primary CPICH. It shows signal quality. The value of EC by NO is greater than minus 15 dB is considered as good, and between minus 15 dB and minus 18 dB it is poor, and the value of EC by NO less than minus 18 dB is considered as very poor. Main reasons of poor EC by NO are poor RSEP, missing neighbors, overshooting, and pilot pollution. Active, monitored, and detected sets. Active set is defined as the set of cells the UE is simultaneously connected to. The ultra cells currently assigning a downlink DPCH to the UE constitute the active set. Cells which are not included in the active set but are included in the cell info list belongs to the monitored set. Monitored set shows probable candidate sectors for handovers. If one of the active cells become weak, it is replaced by a candidate cell having highest signal strength from monitored set. Cells detected by the UE which are neither in the cell info list nor in the active set belongs to the detected set. All the missing neighbors appear in the detected set. These cells must not have high signal strengths, otherwise they will degrade the aggregate EC by NO and lead to call drops. Pilot pollution. When the number of strong cells exceeds the active set size, there is a pilot pollution in the area. Pilot pollution is the detection of many high power pilots as compared to best serving pilot. Pilot pollution ultimately degrades the aggregate EC by IO, leading to call drop. Physical optimization should be done so that there should not be many pilots available at the same spot with equally high signal strengths. GSM drive test parameters. Receive level. Receive level indicates received signal strength in dBm. Receive quality. Receive quality indicates quality of voice which is measured on the basis of BER ranges from 0 to 7, where value 0 denotes the minimum BER. C by I. The carrier over interference ratio is the ratio between the signal strength of current serving cell and the signal strength of the undesired signal components. FER or frame eraser rate represents the percentage of frames being dropped due to high number of bit errors in the frame. It is indication of voice quality in the network. The slide shows the screenshot of a drive test window. Zone architecture. The zone architecture defines the location of zone within the network. When zone is implemented at a high level in the network, OAM, it is called a Network Management System or NMS. While it is implemented at lower levels like E0B, it is called Element Management System or EMS. Depending on the location of zone algorithms, zone architecture may be described as being centralized zone, distributed zone, or hybrid zone. In centralized zone, algorithms are executed at the network management level. Commands, requests, parameter setting, data flow from the network management level to the network elements, while measurement data and reports flow in the opposite direction. The algorithms are present in just a few locations, thereby making it simple and easy to implement. The algorithms can take information from all parts of the network into consideration. it is possible to jointly optimize parameters of all centralized zone functions such that the network becomes more globally optimized. Third-party zone solutions are possible since the functionality can be added at the network management level, where vendor-specific solutions are usually required. The slide shows the centralized zone architecture. In distributed zone, the zone algorithms are run in the network nodes, and the nodes exchange zone-related messages directly with each other. It is more dynamic than centralized zone solutions. It is also a solution that scales very well as the number of cells in the network increases. The slide shows the architecture of a distributed zone. The optimization algorithms are executed in both OAM and the eNode Bs is called hybrid zone. Hybrid zone solution means that part of the zone algorithm is run on the network management level and part is run in the network elements. This solution represents an attempt to combine the advantages of centralized and distributed zone solutions. Centralized coordination of zone functions and the ability to respond quickly to changes at the network element level is one of the advantages of hybrid zone. Hybrid zone is used differently by different vendors. The slide shows the architecture of a hybrid zone. Conclusion: RF planning and optimization plays a vital role in mobile radio network. Without RF planning and optimization, it is merely impossible to roll out and manage a radio network. RF planning and optimization plays an important role in network health as it gives health as well as monitoring of current network conditions.